Good afternoon. My name is Chandra Vidya Sagar, working as assistant professor in St. Peter's Engineering College in EEE department. So today I am discussing about the power system 2 performance of transmission lines. So what is the transmission line? So what is the transmission line means? So we can transmit we are generating the power in the power generating stations. So we can transmit to the consumers. So consumers are staying in far away from the generating station. So here transmission we can transmit in two ways. The transmission the line by using the transmission lines. So we can generate the sub power. We can see here we have the two types of the transmission lines are there. AC transmission and uh, one second. So transmission I have to classified into AC and DC transmission lines. So why means generally we are using the transmission lines AC supply. So day to day life we are using for the power is the AC voltage only. So DC voltage only we are using for the rare cases. So why means we are using AC and DC transmissions. So AC transmission line easily you can transmit from the transmission lines. So DC also we can easily transmit it, but we have to convert AC into DC. What are the power we are generating in the generating station, that is only AC. So that AC we have to again convert into DC. Then again consumer also using the AC transmission. Then again we can convert it into DC into AC. So this is some conversion is required. So but the transmission point of view calculation in the AC we required three conductors. We required here three conductors. So here we required the two conductors. So means conductor point of view can discuss here. So here the conductor size is conductors are increases here. Here we require here two conductors. One is the positive and one is the return negative, means going and return. So this is the case we are using here. But generally we can use AC transmission only. Why means we are generating the power and we can transmit the power by using the AC transmission lines. So now today we will discuss about here performance lines. So in the performance point of view, what we know that here in the performance point of view, you can see definition. So determination of efficiency and regulation of lines. So in the transmission lines we can find out the efficiency and regulation. So then we can perform the transmission lines. So we can work which transmission lines they can working here. So what is the efficiency? We know that general formula efficiency is nothing but so power output, power delivered by power sending into 100. This is the percentage of efficiency. So we know that here we can see here the percentage of efficiency equal to so power delivering. So power delivering by power sent. So this is into 100. This is the percentage. So you can see this is the formula. So we can also write in terms of losses. So we are transmitting. So this is the transmission line. So I am drawing here a small one. This is the one transmission line. So this is the sending end. So this is the receiving end. So this is the current is flowing here, sending end current. So this is the receiving end current. So we can see here. So where we have to connect the generator. So where we have to connect to the source. So that is called as a sending end side. So sending end. So here the sending end voltage is we denoted as a V of S. S means suffix means sending end. So this is the sending end voltage. So where we connecting the load. So this is the load cases. So this is the load. So where we are connecting the load. So this side is called as a receiving end voltage. So we are transmitting the voltage from sending end to receiving end. In the transmission lines we have some parameters are there. So that parameters is resistor, inductor and capacitor. So this due to these parameters, so some losses are there in the transmission lines. So whatever voltage we are sending, the same voltage we are not receiving in the receiving end. So we will reduce that value due to these losses in the transmission lines. So this is the we can find out. We can improve the better efficiency. So means we have to reduce these losses here. So next one is regulation. So what is the regulation definition? So regulation is defined as here. You can see statement here. So a change in receiving end voltage. So whatever the voltage we are receiving here, the voltage will be changing, that expressed in percentage of full load voltage. So from no load to full load. So keeping the sending end voltage and frequency constant. So we can keep this sending end voltage is constant. So what are the frequency flowing in the supply? So we are keeping as the constant. So then we can finding here. So what is the formula for here regulation? So this is the formula for percentage of regulation. You can see here. So VR dash minus VR by, so VR into 100. So this term is the change in voltage. So they are changing the voltage from no load to full load. So no load means this is the VR dash is the no load voltage. So no load means there is no load in the receiving end. So in that case the voltage is the VR dash. This is the full load voltage when we are connecting the full load. This is the change in voltage divided by full load voltage. So this is the formula for the regulation. So now we can okay. So next you can see what is the representation of transmission lines. So we already discussed, we know that here representation, what is the transmission line means. So transmission line is a set of conductors used to transfer electrical power from generating station to load. So we transmit the power from generating station to the load, we require here some conductors. So these conductors we are requiring here, these are the conductors. So these are the conductors. So 3-phase and 4-way lines. So these conductors are supported by some towers. So these are the towers. So these are the towers. Certain level of height we are using here. So we are transmitting this the supporting of the lever. So power is transmitted at very high speed. That means nothing but velocity of the light. So this is the V is the velocity of the light. So we are transmitting the velocity of the light is the weight here. So the transmission line characteristics are by distributed parameters. So we know that here we have the 3 parameters are there: resistor, inductor and capacitor. These parameters are the connection, the way of connecting these parameters. These parameters is called as the distributed parameters. So why means you can see here distributed parameters of transmission lines. This is a transmission lines having the 4 parameters are there. So resistor, inductor, capacitor and conductance. So what is the resistor? Resistor function is to oppose flow of current. So what is the inductor and capacitor? These two will store the energy. So inductor stores the energy in the form of magnetic field. Capacitor will store the energy in the form of electric field. So capacitor is connected between these two conductors. So in these two conductors, the capacitor will be appearing here. So in the line, resistor and inductor will be appearing here. So what is the conductance? Conductance is appearing across the leakage current through the insulation. So we are using here, this is the tower. So in the towers we are using the some supports here, supports. So we are keeping some insulators. So these insulators we are placing the transmission lines. So here conductance will be presenting here. Conductance is means this is the leakage current through the insulants. So insulants here, some any damage there, the current will be flowing here. This is the leakage current. Generally we can consider this is the 0. So generally we are considering as the conductance value will be the 0. So we are considering these 3 parameters in the transmission line. So based on this transmission line, so you can see here, so we know that we already saying that here transmission line is nothing but the wave transformation. So what are the voltage so we are generating here, this is the wave. So we are generating the voltage in the sinusoidal wave. This is the wave formation. So we already discussed now only. So the wave is nothing but, see here, so we can see here so we can see here, this is the frequency. So frequency equal to the velocity equal to we're gonna that velocity, light of velocity equal to frequency into lambda. So I am taking here frequency is constant fixed, light of velocity is nothing but 3 into 10 to the power of 8 meter per second. So we can see here what is the lambda wavelength. Wavelength equal to velocity by frequency. So what is the here 3 into 10 to the power of 8, so divided by 50. So we are getting here approximately 6000 kilometer. So means, so this wave will transmit up to the 6000 kilometers of the transmission line. So this is the wave gauge. This is the, see, electrical signal travels in the form of waves. So this is the wave, the relation between the wave is the frequency and wavelength. So this is the V equal to velocity equal to frequency into wavelength. So how much wavelength will take here, this wavelength here taking here, so 6000 as for the velocity of the light. So we are saying here this is the 6000 kilometer, but in the practical point of view it will not possible. So that will only flow for the depending here. So now we can see here that now we will discuss classification based on line length. So according to transmission length, so we have to classify into transmission line into 3 types. So okay, what is the first one is short transmission lines. Short transmission lines. So the length is less than 80 kilometers. So the length is less than 80 kilometers. We have to consider as a short transmission lines. In the short transmission lines, so we already discussed here. So these are the three parameters. So in this case, the capacitance we are neglecting here. We are neglecting the capacitance. We are only considering for the resistance and resistor and inductor. So next based on the length, so we will say is a medium transmission lines. So medium transmission lines, the length is in between 80 to 160 kilometer. So based on this length, we are considered as a capacitor. So but here the capacitor, the connection of the capacitor, so we had again classified into two types. This is the pi network, next one is the T network. In the pi network, so what is the here the capacitor? So this is the equivalent circuit diagram. So the capacitor is connected both ends of the transmission line. So this is the half of the total capacitance we are dividing into half. So that is connected to both ends of the transmission line. So to see in the T network, the capacitance is connected in mid of the transmission line, the lump sum. So this is the here. So this is the capacitor. So what is the here? So this is the capacitor we are connecting here. So the resistor inductors, so we are dividing here. So this is the resistor and inductors, so we are dividing here. This is the medium transmission line. So next we can go for the long transmission lines. So according to length above 160 kilometers, so we are saying as the long transmission line. So in this case, the resistor, inductor and capacitor is the distributed parameter. So in this case we are using the regressive method to solve this method. In this method we are solving the total transmission length, we are taking this into some small parts of the area, then we will calculating here. So now we will see here short transmission lines. We can see here short transmission lines. So we are considering here short transmission lines. So you can see here, so this is the short transmission line. So this is the equivalent circuit diagram for the short transmission lines. So we are considering here, see here the sending end. So this Vs is nothing but the voltage connected from the generating station. So that is called a sending end. This is the load where we connecting the load. This is the receiving end voltage. So this is the sending end current. This is the receiving end current. This is the phasor diagram from the short transmission lines. So we can see here from the vector diagram. So we know that here, so Vs cos pi s equal to, so Vr cos pi r plus Ir r. So this is the, we can consider as the first equation. So from the, you can see here Vs sin pi s equal to, so Vr sin pi r plus Ir x. This is the 1b. So now we can see in the two equation from the vector diagram we are getting this equation. This is the here, this is the vector diagram. I am taking here receiving end voltage as the reference phasor. This is the receiving end voltage, the referencing phasor. So we know that this is the, we are considering this is the lagging load. So load is the lagging load, means the voltage leads the current. This is the receiving end voltage. This is the drops across the R and JXL. So this is the IR and this XL. So this is the equation. So I am squaring and adding this equation. So we are getting here equation, we can see here. So Vs square equal to, so Vr square plus, you can see here Vr square plus 2 IR r. So Vr cos pi r plus 2 IR x Vr sin pi r plus IR square Rx. The IR square Rx we are getting here as a IR square of R square plus X square. So we are getting here. So I am adding these equations A and B and squaring and adding these equations, we are getting, this is the equation. So you can see from here, from this equation Vs equal to, you can see here, so Vs equal to, so Vr square root of 1 plus 2 IR r by Vr cos pi r plus 2 IRX by Vr sin pi r plus, you can see here, so IR square by Vr square into R square plus X square. So this is the equation. From this equation we are getting the Vs value. So in practice, the last term we can go in the practical point of view. This last term under the square root sign is generally negligible. So we are negligible this equation. So then we are writing here. So equation Vs equal to, you can see here I am writing here. So Vs equal to, I am writing here. Again you can see here equations. I am neglecting here last term. So in practice this last term we are neglecting here. So we are writing here equation, you can see here. So Vs equal to, so Vs equal to, you can see here. So Vr into 1 plus 2 IR R Vr cos pi r plus 2 IRx by Vr sin pi r power 1 by 2. So you can see here from this equation the term with this simple, so I am simplifying this one in the simple brackets is small, this is the simple bracket, this is the simple brackets. So this will be considering as a small, you can see this is the considering as a small compared to the unity. So the by using the binomial expressions, the Vs is approximately equal to Vr plus IR R cos pi r plus IRx sin pi r. So this is the voltage. So in these simple brackets, so this value is very small compared to unity. So then we are simplifying this equation. So I am getting here Vs by using the binomial expression. So Vs is approximately equal to Vr plus IR R cos pi r plus IRx sin pi r. Here Vs is the sending end voltage, so Vr is the receiving end voltage. So here you can see the correspond to the particular current and power factor condition. So the Vs is the particular power factor conditions we are considering here. So we can see here in the definition, we can see here regulation. What is the regulation in the no load condition? We can see here. So in this condition, we can see here regulation, how we can find out the regulation. So in the no load condition, here there is no load, so means Vr dash is equal to the Vs. So Vr dash is equal to the Vs. So now we know that the formula for regulation, so percentage of regulation equal to, so we know that no load voltage minus full load voltage by full load voltage into 100. So in this case short transmission lines, so we don't have it is no load, so the no load, we are neglecting the no load condition, means so Vr dash no load voltage is approximately equal to the sending end voltage, means the regulation is nothing but the, so Vs minus Vr by, so Vr into 100. So this is the regulation of the short transmission line. So I am taking here this regulation in the per unit value. So we are considering this the regulation into per unit values. So I am taking here regulation into per units values. So Vr equal to, so IR R by, so Vr cos pi r plus IR x by Vr sin pi r. So this is the per unit regulation. So regulation per unit, regulation per unit. So you can see here. So regulation per unit equal to, so this is the regulation per unit. So this is the formula. So that equal to, so small Vr cos pi r plus small Vx sin pi r. So this is the regulation in terms of the per unit value. So here we can consider here per unit values. So everything length, everything we are considering the per kilometer. So per kilometer we have to consider here. So we know that here transmission line, I am considering here this is the transmission line, nothing but the 4 parameters are there. So 4 network element is there. So in this case we are considering you can see here the for terminal passive network for voltage and current on the receiving end, sending end related to the following equations. So we know that here, so 2 port network, so Vs equal to, so A Vr plus B IR So is equal to P VR plus D IR. So these are the equations. So we know that here A, B, C, D is the constants of the network. For the transmission line also have 4 terminals of the network. So it is now decided for the constant to for transmission. We can decide what is the A value, B value, we can find out here. So we can find out here A value. So what is here? The current will be the 0. So when I am taking here IR is 0 means, so this is the open circuit. I am considering the load, there is no load means that is the open circuit condition. So in that condition, so IR equal to 0 means A equal to, so Vs by, so VR. So this condition is IR equal to 0. This is the open circuit condition. In these conditions means this is the voltage and voltage, this is the dimensionless. So A is the dimensionless. So again from I am taking here IR equal to 0 means C equal to IS by VR. So this is the condition for IR equal to 0 condition. So this is the open circuit condition. So C is nothing but, so current is nothing but the amperes. So this is the voltage, units for the voltage. So receiving end voltage. So this is nothing but the admittance. So this is nothing but the admittance. So this is the mho unit. So next you can see for the, so we have to calculating for the current. Voltage will be 0 means when the voltage will be 0 here, so the receiving end I am taking here the short circuit. So in the short circuit means I am taking here, so B equal to, so Vs by IR. So in this condition receiving end voltage will be 0. When will be 0 voltage? So the circuit will be the short circuit condition, so the voltage will be the 0. So here we can see here voltage having the units voltage V, and the current having the units as the ampere. So this is nothing but the impedance. This is nothing but the impedance. So this is the impedance units is ohms. So next you can find out the D. So D equal to Is by IR. So when VR equal to 0, so ampere by ampere cancel me, this is the dimensionless. So A, B, C, D, this is the dimensionless. So we can comparing this equation with, these are the equations. So these equations we are comparing with this simple circuit. You can see here this is the network condition. So I am considering this is the this equivalent circuit diagram is the equivalent circuit diagram. See, this is the equivalent circuit diagram. So I can see here Vs equal to here. So you can see here Vs equal to, so what is the condition here? So VR plus IRZ. So in the short circuit condition, this is the series. So IS equal to IR. So here this is the you can see this is the equivalent circuit diagram. So this is the simple circuit I am drawing here. We are explaining here. This is only series circuit. We don't have any parallel parameters. Means in series whatever current will be giving here sending end, the receiving end also we are getting the same voltage. This is the IS equal to IR, VS equal to VR plus IRZ. So we are comparing here, and what is you can find out the A parameter. You can see here I am comparing this equation with this equation. So VS A VR plus B IR. So what is the A value here? So A value equal to 1, here B value equal to Z. So now I am comparing with this IS equal to IR with IS equal to C VR plus D by R. So what is the here? C value there is no VR term means C will be the 0 and D will be the 1. So here there is no value, this is the 1. So this is the values of the this is the values, this is the calculated values for the short transmission lines. So we know that conditions. So this is the parameters AD minus BC equal to, this is the 1. So this equation will satisfy. So whatever the values we are calculating, so this will be the exact values we are getting here. So I am substituting here AD minus BC equal to 1. What is the A value is 1, D value equal to minus B value is Z, C value equal to 0. So this means 1 into 1 1, 0 into anything that is 0. So we are getting the 1. So these are the transmissions. So what are the values we are find out these parameters A equal to B, we are calculating this ABCD parameters value is the true for the short transmission line. So we are calculating here ABCD parameters. So in these parameters we will see for a small example. I am considering here a small example. So we can see here this is the example how we can do this, solving this example. So you can see the problem. A single phase overhead transmission line delivers 11,000 kilowatt. So delivers means you can see this is the power. So power is given 1100, delivering power. So P, so we can say this is the P delivered. So instead of I am writing here delivered power delivered. We can say power delivered. So how much they given? 1100 kilowatts and at 33 kV at 0.8 pf lagging. So where they given this is the delivers means the receiving and the voltage will giving here VR value. So VR value is given 33 kilovolts. So here the power factor is nothing but the receiving end power factor. So this is given by 0.8 lag. See, they given total resistance and inductance of the line are 10 and 15 ohms. So they given here Z bar. So Z bar is nothing but the R plus JX. So that is given plus 10 plus J 15. So this is the they given data. So what we have to find out, first one we can find out the sending end voltage Vs. Second one we can find out the sending end power factor, that is the cos pi s. So next is the third one is the efficiency of the transmission lines. So I had to find out these values. So before going to this one, so we can see this is the phasor diagram. We can see here this is the these are the phasor diagram I am drawing here. So I am taking as the reference is the receiving end current IR. This is the VR and here. So we can from this equation, so we can calculate here problems. You can see the solution how we can calculate here. So receiving end voltage and current here we can see here. First one we can find out the sending end voltage Vs. We have to calculate. We have to calculate the Vs. So before going to Vs, so I am connecting here VR bar. So I am representing everything in the vector representation. So VR bar equal to VR plus J0. So that is the 33,000 volts. So next we can find out the I. Before find out the current, so receiving current or anything same, we can find out the current means what is the current value. So current value we can calculating here. So we know the power. So power, how much they given power by, this is the single phase. Single phase we know that power formula equal to power equal to VRI cos pi r. From here I am writing here I equal to P by VR cos pi r. What is the P value? 11,000 kilowatt divided by, so VR is 33 kV into cos pi is 0.8. So we are getting here 41.67 amperes. Now we can representing here in the current in vector representation I equal to I cos pi r minus J sin pi r. So cos pi r is nothing but how we get the sin pi r means, so cos pi r value is given is 0.8. From here we can find out the pi value. So then we can substitute in the sin pi r. We are getting sin pi r value is 0.6. So I am substituting here 41.67 into 0.8 minus J 0.6. So we are substituting here, we are getting the values is 33.33 minus J 25 amperes. This is the current for the I. So this is the current for the I. So we know we are finding here what is the sending end. So we are finding the first one. So before going to, we can calculate this one. So what is the here next we can find out here sending end voltage. Sending end voltage means Vs equal to, so VR plus, so VR plus IR bar plus Z bar. So this is the VR bar. So this is the Vs bar. I am finding everything in the vector representation. So what is the VR value is 33,000 plus, what is the IR value? 33.33 minus J 25 into Z value is, we know that 10 plus, so J 15. So we can solve this one. So I am solving this one, 33,000 plus, I am multiplying with 10. So how much we are getting here? 333.33 minus J 250. So next we can multiply with J 15. So J 15 we are multiplying here plus J. What you can see here 33.33 into J 15. So we are getting here 500 J 500. So here see J square value. J means J into J means J square. So we know that J square J value is nothing but J square value is nothing but the minus 1. So minus of minus, what will be getting the plus. 25 into 15, what we are getting here? 375. So now we are solving here, we are getting here 33,708.3 minus, I think, plus J 250. So this is the voltage. So but we required here voltage in the, this is the vector representation, but we required here magnitude representation. So we are getting the magnitude. We know that for magnitude of Vs equal to square root of, so 33,783 square plus 250 square. So we are getting here, this is the value 33,700 volts. So this is the sending end voltage. This is the sending end voltage. So this is the first find. We can find out the sending end voltage we are finding here. Next we can find out the sending end power factor. So before finding the sending end power factor, we can see here from the vector diagram, we can see here. So this is the phasor, this is the voltage angle for the pi r. So now we can find out what is the pi s here. So from this second one, you can see here, we can find out the, so second one you can find out the sending end power factor of the sending end. So before finding the find out factor, we had to find out the pi s. So how we can get pi s is pi r plus alpha. So this is the alpha, the angle between here. So this is the alpha. Alpha is nothing but the angle between the VR and Vs. So what is the alpha we are getting here? Alpha equal to, so tan inverse, you can see here we are getting here alpha equal to tan inverse. So 250. So in the previous class we are getting the voltage 250 by 33,708.3. So we are getting here alpha value equal to 0.42. So 0.42 degree we are getting here. So I am substituting here pi s equal to pi r. How we getting pi r here? So cos pi r equal to, so 0.8. From here pi r equal to, we are getting here cos inverse of, so 0.8. I think that will be 36.87 degrees. So I am adding here 36.87 degrees plus 0.42 degrees. So how much value we are getting here? I think 37.29. 37.29 degrees. So you can see here in the figure diagram. So this is the angle from reference to voltage. This value we are finding here pi s. Then we have to find out the power factor, means cos. So pi s. So cos of 37.29. So we are getting here 0.79 lagging. So this is the power factor value. This is the 0.79 power factor value. So next, what is the third one? You can see here. Third one, we have to find the transmission efficiency. So before we have to find out the transmission efficiency, so we can find out the output power. So Vs equal to, we know that power. So we can find out the first losses. So you can see here, this is the third one. So I am finding here third one is the losses. So losses equal to I square R. So what is the R value? 1.67 square into R value is 10. So we are getting here losses. Losses we are getting here 17,364 watts. So I am converting this is into kilowatts. 17.364 kilowatt. So this is the losses. So now we know that the receiving end power. Then we can find out the sending end power. How we get in the sending end power? PS equal to, so receiving end power plus losses. So what is the receiving end power is 11,000 kilowatt plus 17.364 kilowatts. We are getting here 11,017.364 kilowatt. This is the sending end power. So we know that the efficiency formula, efficiency equal to power, receiving power by sending end power into 100. So you can see here what is the receiving end power? 11,000 divided by sending end power 11.364 into 100. So we are getting the efficiency. So efficiency will be we are getting here approximately 98.45%. So this is the way we can calculate the simple way. Simple way we can calculate the transmission line. So once again we are repeating here. So transmission line, we have to find out the performance here. So based on the efficiency and regulation, so we have to find out the performance of the transmission lines. So transmission lines classified depending upon the based on the length. So we can doing here. So this is the way we can calculate the short transmission lines. So thank you for today class. So next class we will discuss about the medium transmission lines. Now